Three distinct technologies, data materials, wind energy, and lab-generated life, mark the modern age. Yet silkworms continue weaving miracles in their own way. Why focus on insects when science can generate life? At first glance, it seems primitive. But in reality, a bio-industry is emerging across the still plains of China, governed by scientific precision. Industrial discipline guides the production cycle, and one can observe the precision involved. But this is just the beginning. One can notice how a cocoon, small enough to fit in a hand, holds an immense chain of value. It bridges traditional fashion and medicine to advanced biotechnology. It gets more complex further on. Because silk is no longer a symbol of the past, it is redefining the fabric of the 21st century. It is visible how nature and technology become one here. The secret weapon of the future is being spun by this tiny creature. The story of this integration proceeds calmly. 500,000 tons of plastic microfibers are released annually by the synthetic fabric industry, seeping into oceans and poisoning water sources. Amidst this global environmental issue, China is witnessing the powerful revival of a Silk Road tradition spanning 5,000 years. But this is just the beginning. Why rely on an ancient biological process in the age of advanced polymers? At first glance, it seems inefficient to depend on insect larvae, but in reality, the resulting material offers unmatched physical resilience. The threads spun from the Bombyx mori silkworm are as light as air yet several times stronger than steel by weight. The process is only gaining momentum. One can notice that the natural fiber decomposes completely without leaving behind microplastics. It integrates back into the environment without a trace. Consequently, the country produces more than 60,000 tons of raw silk every year. This volume accounts for nearly 70% of global output, generating over $5 billion United States dollars in export revenue. And this is not the limit. The industry provides jobs for millions of rural workers, weaving a nation's economic and cultural identity. It is visible how the material moves from high-tech factories to the prestigious runways of Hermès and Dior. Thus, China transforms this ancient fiber into a symbol of the biomaterial revolution in the high-tech era. 20,000 square meters is the operational footprint of each modern silkworm farm in Sichuan. These facilities function as self-contained industrial ecosystems beneath heavy insulated roofing. An integrated microclimate control system ensures a stable environment year-round, regardless of external weather. But this is just the beginning. Inside, rows of multi-level rearing houses stand arranged in strict parallel order. Why is the internal climate regulated with such extreme rigor? Deviations might seem minor to an observer. However, maintaining an ideal temperature of 25 to 27 degrees Celsius is vital for the metabolic rate of the larvae. One can notice how digital sensors continuously hold humidity at around 80%. Data flows to a central system that adjusts parameters in real time without human interference. Every square meter houses 1,500 to 2,000 silkworms. They grow in perfect synchronization within a space where airflow, lighting, and air purity are precisely calculated. It gets more complex further on. At first glance, the aisles seem quiet, but in reality, automated ventilation fans rotate ceaselessly. Sterilizing floors and monitoring systems operate non-stop to exclude pathogens from the environment. It is visible how technology and life move together in absolute precision, turning the farm into a large-scale biological laboratory. The cycle continues here, providing the optimal conditions for the next stage of development. Billions of silkworms operate within a closed production chain defined by absolute precision. Their nutrition is strictly controlled, consisting solely of mulberry leaves. Specialized farms are located right next to the rearing facilities to ensure the highest nutritional value reaches the larvae. This proximity guarantees freshness from the moment of harvest to the feeding tray. But this is just the beginning. It is visible how mechanical harvesters or farmers carefully select the middle and lower sections of the branches every morning. Why focus on these specific sections of the plant for collection? It would seem easier to harvest the entire branch efficiently. These areas hold protein and chlorophyll levels at their absolute peak, which are essential for the colony's rapid development. One can notice how the leaves enter the processing area immediately after cutting for sorting. At first glance, air drying with cool natural airflow seems simple, but in reality, it prevents fatal moisture complications in the digestive systems of the larvae. Silkworms never drink water throughout their entire life cycle, absorbing liquid only through the leaves. The process is only gaining momentum. Even a thin layer of dew acts as a poison, causing severe bloating or widespread disease outbreaks. Therefore, each mulberry leaf is treated as a standardized nutritional unit. This biological foundation allows the colony to spin the purest silk threads on Earth. The diet is now perfectly balanced for the next stage. 25,000 times its own body weight is the amount of mulberry foliage a single silkworm consumes. Why must this intake occur within a lifespan of only roughly 25 days? At first glance, it seems like simple gluttony, but in reality, this intensity is biologically necessary to spin the purest silk threads on Earth. Once the harvested leaves are completely dried, transport systems move the material to the rearing area. One can notice how thousands of trays are neatly arranged in stacks inside the climate-controlled rooms. Millions of worms enter their growth stage here, with each container holding hundreds of larvae at the same developmental phase. But this is just the beginning. Because digestive capabilities change, leaves are cut into defined sizes depending on the silkworm's age. Young larvae eat soft leaves chopped into tiny 1/2 centimeter pieces, while mature worms need thicker strips about 3 to 4 centimeters long to stimulate silk production. And this is not the limit. Therefore, feeding occurs 4 to 5 times a day at fixed intervals to synchronize metabolism. It is visible how the automated microclimate system adjusts the environment after each meal. The humidity drops to 70% to prevent mold, then rises back to 80% to aid digestion. The cycle maintains its rhythm, accompanied only by the gentle rustling of leaves under the soft light. 24 degrees Celsius is the precise limit to which the automated system lowers the air temperature. Simultaneously, the equipment stabilizes the humidity at exactly 75%. One can notice how, under the diffused light, the bodies of the silkworms turn a translucent white. It seems like a simple biological change, but in reality, this visual shift signals the critical readiness of millions of larvae to spin. But this is just the beginning of the transformation process. Why are these atmospheric conditions controlled with such rigidity? The entire rearing hall shifts into a slower rhythm of anticipation. These specific parameters are required for the silk glands to work at their absolute full capacity without deviation. Each silkworm secures itself on the multi-layered bamboo or plastic racks. It is visible how the head moves in a graceful figure-8 motion to distribute the material. The liquid protein solidifies instantly upon contact with the air, forming a thread only 10 microns thick. Everything only gets more complicated as the network of fibers grows. A single continuous filament can stretch up to 1 to 200 meters in length. Over the next 48 to 72 hours, synchronized movements weave a dense sea of white cocoons. The camera glides along the rows where each capsule weighs strictly 2 to 3 grams. The material is ready to move to the next processing phase without haste. 2 to 3 times the strength of domestic threads distinguishes the golden fibers produced in the northern regions. While the Bombyx Mori farms in southern China are covered in millions of shimmering white cocoons, the northern Tuza farms quietly continue a different chapter of the silk industry. This sector is known as the symbol of wild silk. But this is just the beginning. Why do these facilities utilize semi-open structures? It seems that a sealed laboratory would offer better control over the delicate insects. However, blending natural light with automated climate systems is necessary to recreate the exact conditions of the forest habitat. 26 degrees and 70% humidity are strictly maintained in climate-controlled cages for peak vitality. One can notice how the moths preserved from the previous season are released onto hanging racks, where they fly and mate naturally. 3 to 5 days later, farmers intervene with bamboo sticks. At first glance, shaking the frames seems like a crude action, but in reality, this movement disperses pollen and significantly increases fertilization rates. The larvae are then raised separately. It gets more complex further on. One can notice the golden hue developing as the insects absorb tannins from their exclusive diet of oak, elm, and wild apple leaves. 50 to 60 days is the duration of the growth cycle, which is nearly twice as long as that of domestic silkworms. Instead of being harvested early, the creatures are allowed to complete their metamorphosis to preserve genetic diversity. One can notice the dense fibers and natural luster that make this the silk of the forest. The material is now ready for luxury craftsmanship. 72 hours after the silkworms cease spinning, the farm shifts its rhythm from silence to urgent activity. Why is the moisture level strictly monitored before the harvest starts? An ivory white hue covers the racks, suggesting readiness. But without a level below 12%, the cocoon remains unstable for processing. Hardness must reach between 0.3 and 0.4 newtons. One can notice how workers verify these parameters on each frame, but this is just the beginning. Compact mechanical systems have replaced the manual labor of previous eras. In the past, separating 10,000 cocoons required 8 hours of delicate work. At first glance, it seems that only fingers could handle such fragile material, but in reality, modern automation operates with superior care. A hydraulic hoist with a capacity of 300 kilos lifts the spinning rack smoothly. The equipment gradually lowers the load onto conveyor belts, moving at 10 meters per minute. Semi-automatic separators engage 80 Hz vibration and precise air pressure. It is visible how the machine isolates tens of thousands of cocoons within minutes. The 10-micron silk fibers remain completely undamaged during this action. The process is only gaining momentum. Because of this precision, waste material drops to below 2%. Harvesting efficiency increases tenfold as the hum of machinery blends with the faint rustle of dry shells. The mechanical heartbeat of the production line pulses without pause. The raw material is now ready for the subsequent stage of refinement. 0.4 millimeters is the precise shell thickness required to qualify a cocoon for the high-grade silk production line. After leaving the farm, trays of cocoons arrive at the manual sorting area, where layers are spread thin on long bamboo tables covered with fine mesh. Why does the sorting process rely so heavily on human eyes and years of experience? At first glance, automated scanners would seem more efficient for processing the raw harvest, but only natural light allows workers to evaluate the uniformity and luster with the necessary precision, ensuring that every selected cocoon is perfectly rounded and smooth on the surface. The process requires absolute strictness to filter out defects. Only those cocoons falling between 0.4 and 0.6 millimeters in shell thickness are selected for the next stage, where the purity of each thread must reach near-perfect precision. Immediately after sorting, the qualified cocoons are sent to the heat treatment area to determine the integrity of the fibers. Workers must halt the life cycle of the larvae inside using one of 3 specific methods: steam heating, hot air drying, or immersion in water heated from 85 to 95 degrees. This intervention prevents the larvae from maturing into moths. because if the moth emerges, it pierces the cocoon structure, destroying the continuity of the valuable filament. Each batch is gently stirred to ensure even heat distribution without deforming the outer silk layer. The heat not only stops metamorphosis, but also sterilizes and stabilizes the silk protein, keeping the inner fibers soft, strong, and long-lasting. But this is just the beginning. From the heat treatment area, the dried cocoons transfer directly to a row of warm water basins, releasing gentle steam. At first glance, this looks like a simple washing process, but in reality, it is a calculated chemical awakening of the material. Water maintained between 65 and 90 degrees Celsius acts on the sericin layer coating the silk fibers. A light stirring system keeps each cocoon fully submerged, allowing the shell to gradually soften. One can notice how the surface takes on a glossy, misty sheen as it absorbs the moisture. When touched, the cocoon is no longer brittle, but slightly elastic, a clear sign that the inner fibers are ready for the most delicate stage. The factory atmosphere now moves in harmony with the rhythm of steam and metal. The gentle simmer of water blends with the steady hum of spinning reels, creating a mechanical symphony. In basins maintained at 90 degrees, slow rotating circular brushes remove the remaining sericin layer while searching for the silk's loose end. This thread is only 10 microns thick, making it almost invisible to the naked eye. Once the end is found, workers quickly guide it into the reeling machine, where synchronized drives pull the strands in perfect rhythm. Threads from 5 to 10 cocoons are combined, evenly stretched, and wound onto spools at a speed of 300 meters per minute. It is visible how each rotation catches the light with a silvery shimmer as the fine silk flows through the rollers like liquid metal born from the breath of the cocoons themselves. On average, one cocoon yields about 1,000 meters of thread. Roughly 3,000 cocoons are needed to produce just half a kilogram of raw silk, which serves as the foundation for the world's most exquisite fabrics. And this is not the limit. To become flawless, the shimmering threads pass through spinning machines. Here, each fine strand is twisted by spindles rotating at 6,000 to 8,000 revolutions per minute. In the quiet space, the hum of rollers and the soft hiss of steam fill the air as clusters of delicate filaments intertwine. They form a uniform, durable structure that still retains the natural softness of the silk. At this stage, artisans may blend fibers from different cocoons to create variations in thickness or distinctive patterns. The artistry lies in the twist ratio. Wool or alpaca requires a tight spin to prevent breakage, whereas silk, with its long, smooth fibers, needs only a gentle twist. This is just enough to unify the strands while preserving the graceful drape and signature luster. When the spinning reels come to a stop, the silk's journey of refinement continues to the degumming area. In basins kept at 60 to 70 degrees, a mild alkaline solution slowly dissolves the outer sericin layer. Beneath the soft mist, the threads reveal a luminous, glassy core that feels almost weightless and smooth to the touch. Freed from its coating, the silk awakens, transformed from a raw fiber into a living, pure, and radiant material. To add color to the journey, the threads are taken to the dyeing section, where steam and herbal scents blend in a warm atmosphere. In deep baths, maintained at 80 to 90 degrees, natural dyes extracted from indigo leaves, pomegranate peels, rosewood, or madder roots slowly seep into every fiber. One can notice the pigment spreading like wisps of smoke through the water. The silky bundles soak for 4 to 6 hours, gently stirred to let the color reach the core, creating a clear tone and lasting vibrancy. In traditional workshops, this ancient dyeing craft remains the soul of ikat and brocade patterns, where every shade is born from the earth. It gets more complex further on. After absorbing the natural dyes, the shimmering silk threads move to the weaving area, the final stage of their long transformation. Inside a space glowing with reflected light, the looms begin to move, their rhythmic clatter echoing like the heartbeat of the factory. Steam, metal, and the soft gleam of silk merge into an atmosphere that feels both alive and meditative. Depending on purpose and tradition, the silk may be woven on handcrafted bamboo looms, where artisans guide each warp and weft with remarkable precision. Alternatively, industrial machines operate with millimeter accuracy. Every gentle pass of the shuttle is a pulse of creativity and patience, turning fragile threads into flowing forms. In modern workshops, thousands of fibers move in perfect harmony under digital control, interlacing and shimmering under the light. Each strand becomes part of a larger pattern, fluid yet precise, soft yet strong. Here, silk is not only woven into fabric, but into a story of resilience and artistry. Human skill and mechanical rhythm unite to give birth to something timeless, breathing life and elegance into the world of textiles. Thousands of years define the operational history of this biopolymer. The material originates from the biological output of a tiny creature, forming a continuous filament. One can notice the shimmering glow on the surface as light hits the fibers. But this is just the beginning. Why is this organic thread still critical in the age of technology? Artificial polymers are widely available for production, yet the unique triangular cross-section refracts light, creating optical properties impossible to ignore. At first glance, the textile feels soft, but in reality, it is incredibly strong relative to its thickness. The protein chains resist breakage under high tension. This durability preserves the structural integrity of the fabric. It does not end at this stage. Engineers study this natural geometry to guide the development of future materials. The process concludes here, leaving the material ready for the next phase.